Okay, we just have a couple of other details to wrap up before we can dive in and start really talking about some physics. We need to talk about what a coordinate system is, and we need to talk about different types of physical quantities that we might encounter as we go through this semester. So the first bit that we need is we need to understand a coordinate system. And so, a lot of times you've run into coordinate systems before, right? And in math, a lot of times we use the x, y coordinate system. And we will in this class too. But let's just talk generally about what does it mean to have a coordinate system? Well, a coordinate system allows you to locate something. And as an example, let's talk about a question. Where is Greeley? Well, how are we going to answer that question? Well, we need to know a few different pieces of information. We need to know it's about 55 miles northeast of Denver. Okay, so this helps us to locate where is Greeley. But let's be real specific about this. What are we saying when we say this? We're saying, how far are we, in what direction, and from where? That's the basis of what we need for a coordinate system. And so in this case, our XY coordinate system tells us the same thing. Here we have two different directions. We're saying we've got X and we've got Y. How far? Well, we'd want to include a scale, 1 meter, 2 meters, for example. Maybe this is 1 meter, 2 meters, right? So we'd want to include a scale. So now we know how far. And in what direction? Well, that's X direction or Y direction. And typically we use positive to mean to the right or up. And we need negative to mean to the left or down. So how far and in what direction? Positive X, positive Y, negative Y. And from where? Well, if we're using an XY coordinate system, we always use the origin as our from where. So we're measuring all of this stuff from where the x-axis meets the y-axis. This is what we need for a coordinate system. These three pieces of information together form a coordinate system. And the origin is what we mean by from where. And in the xy coordinate plane, it's where the x-axis meets the y-axis. Not too bad. Okay, so coordinate system then, it gives us a basis for which we can talk about all kinds of different things. One thing we're going to encounter a lot is displacement. And displacement means sort of, the change in your initial position to your final position. And we're going to represent that like this. So delta x means change in x, or change in position. And so delta anything means final minus initial. We could talk about the y or the x-axis, right? Change in anything means final minus initial. This little squiggly guy, right? Change in this squiggly guy is final squiggle guy minus initial squiggle guy, whatever. The change in the amount of money that you have in your pocket is the money you ended up the night with minus the money you started with. So this goes for almost anything. You've probably run into this before. This is, of course, Greek letter, delta. So delta x means change in x. Okay, couple of different ways that quantities might manifest themselves in nature. Some quantities are scalars, and they just need a number for a complete description. Examples are time, temperature, and mass. So while scalars do not have direction, they can be positive or negative. So, for example, let's look at mass. The mass of my calculator, it might be 200 grams. Okay, so let's say 200 gram calculator. 200 grams in that direction. That doesn't even make sense. How can mass have a direction? It's 4 degrees outside in that direction. I don't know what it means. Right? Some quantities just don't need a direction. But maybe you're thinking, well, what would need a direction? Well, some things just need a direction. Some things need a direction and a magnitude or a size for a complete description. For example, what if I told you I'm going to walk 2 feet? I'm going to walk 2 feet from where I am right now. Does that tell you where I'm going to end up? No, it doesn't, because direction is important. Am I going to walk 2 feet that way? Or am I going to walk 2 feet that way? Or 2 feet that way? The result will be different. And so that's why displacement, which is what I just described, is a vector. So for some things, direction matters. I'm going to push on this calculator. Does that tell you which direction it's going to go? Does that tell you what its motion, what its subsequent motion will be? No. If I'm going to push on this calculator, you need to know what direction I'm going to push in order for that to make really any sense at all. Okay. So, force is another quantity that just needs direction. It just needs direction. Force, acceleration, displacement. We're going to find that velocity is another example of a vector. So lots of things in nature are vectors, and lots of things in nature are scalars. And it's not up to us to decide. It just is, right? There's just something about mass that doesn't need a direction. There's just something about force that needs a direction. So some quantities just naturally need a direction for a complete description, and some quantities just don't. So if it's a vector, it needs a size and a direction, a number and a direction. The size, or the number, that is called the magnitude. And magnitude's a word that trips students up sometimes. Any vector can have a magnitude. Whether we're talking about force, acceleration, displacement, velocity, all of those are vectors. They can all have a magnitude. So magnitude isn't some specific thing that goes with a specific type of vector. Every vector has a magnitude or a size and a direction. A magnitude and a direction. We will represent vectors with an arrow. And so the length of the arrow is proportional to the magnitude. So if I had two vectors and I was drawing them on the same piece of paper, and one of them had a length like that, and one of them had a length like that, then we'd say, aha, well, this vector has a greater magnitude than this one does. Why? Because it's longer. And so it should be proportional. We'd need to set a scale or something to say exactly how long it should be. But generally speaking, the length of the arrow is proportional to the magnitude. The direction of the arrow is the same as the direction of the vector. And so, in other words, this is a vector that points in this direction. This is a vector that points in this direction. We give it a name. In this case, I am cleverly calling this F. Maybe it's a force. Force is a lovely vector. In which case, if this was a force vector, it would represent the force applied to some object at this point right here. We give it a name, in this case F, and we write a little arrow over the top of it. The little arrow over the top of it here, that indicates that we are talking about a vector. If we are working in one dimension, we can drop the little arrow and use plus or minus to indicate direction. So, for example, if I know I'm on the x-axis, then my two choices are that direction or that direction. If it's in that direction, it's positive. If it's in that direction, it's negative. But it's all on the x-axis. And so, basically, if we are in one dimension, we can just drop this little vector sign and we're all good. Displacement is a vector, as I just mentioned. So let's say I have a particle that moves from point A to point B. The particle's distance is traveled is much greater than the magnitude of its displacement. Why? Because displacement is a change in position. It is an arrow that points from where I started to where I ended. And since it's a vector, it has a magnitude and a direction. So looking at this little path here, the distance traveled would be the total length of this line right here, whereas the displacement would simply be the magnitude would just be the length of this arrow, and the direction would be pointing directly from A to B. And these are different ideas, right? And you might say, well, they're so similar. Why do we care about the distinction here? Well, they're different ideas, right? One of them includes a direction, and it says just where did you end up compared to where you started. Whereas one of them says, well, okay, but how far did you go as you traveled, right? So they really are different things, and so we really do need different ideas to express them. Let's do a quick example to see how we might use these things. Okay, here's an example. Jane walked 3 blocks east and then 4 blocks north. First of all, define a coordinate system, then what was her displacement, and finally, how far did she travel? Okay, first of all, define a coordinate system. Well, in this case, we can just use a grid, and maybe we won't use x, y, since it's given us east and north. So let's write a coordinate system that looks like this. There's north. There is east. And we should be marking these in blocks. And it looks like we got, we need 4 blocks at least. So. Okay, there we go. I have defined my coordinate system. I have an orange, I have an origin, and I have directions with distances. Great. That is my coordinate system. Okay, what was her displacement? Well, first, let's draw her, well, these are really 2 displacements. First, she walked 3 blocks east. So let's draw the path that she traveled on first. So first, she walked 3 blocks east. That's going to look like this. And she goes 3 blocks east. And then she walked 4 blocks north. Okay. So first she walked 3 blocks east, then she walked 4 blocks north. Now recall that the displacement is an arrow. It points from where she started to where she finished. So the displacement then would point right here. That is her displacement vector. We will give it a name, D. It has an arrow to indicate it as a vector. It points from where she started to where she finished. Now we can do a little bit of trig in order to figure out the length of that displacement arrow. Well, we've got a triangle here, and now we could kind of recreate this if we wanted to. We might not have to, but now we just have a triangle, right? And a lot of times in this class, this is what we're going to try and do. We're going to take a physics problem, which really, this business about Jane walking, that's really a physics problem. And we're going to turn it into a trig problem. In this case, we have a trig problem where we have a triangle with one side 3 and one side 4. Now, I picked these numbers because they're very convenient. This is a Pythagorean triple. If you were to go ahead and do the math, a squared plus b squared equals c squared, then you would find that the square root of 3 squared plus 4 squared equals 5. Well, square root of 3 squared plus 4 squared equals 5. This is the 3, 4, 5 triangle. A Pythagorean triple. You can always use the Pythagorean theorem to figure out your hypotenuse there. So, we've got then the magnitude. So the magnitude then is 5 blocks. So for displacement, we have 5 blocks. But I'm not done. This is the magnitude of her displacement, but it's a vector, so we need a magnitude and a direction. Now the direction, we could say, well, it's sort of a northeast-ish, and that would work. That would work. But you know, if we really wanted to be more specific about it, we really should find an angle. That's the way to specifically say what exactly is the direction. So let's call this theta then. And now we can do a little bit of trig. Which trig function would you use? Well, it really doesn't matter because we've got all 3 sides. We could use any of them. For me, I thought of using the tangent first. So we know the opposite and the adjacent. So I'm going to write theta equals the inverse tangent of opposite 4 over adjacent. And then I'm going to run my calculator, and I get 53.1 degrees. Okay, so now we're ready to finish writing down what the displacement was. Right? We weren't done here because we just had a magnitude. We need a direction also. So 5 blocks. 53.1 degrees, and we could say that that is north of east. That is the displacement of Jane. That's her displacement. Great. Notice that we need 2 pieces, direction and magnitude. How far did she travel? Now, how far did she travel is a vector. It says, how far did she travel? I mean, it's pretty self-explanatory. Well, she went 3 blocks, then she went 4 blocks. So she traveled 7 blocks. Distance traveled, then, 7 blocks. Not too bad. Again, these are different ideas, so we need different math for different ideas. You know what we just did here? We actually just added vectors, right? I asked you what was her final displacement, but I gave you two displacements, right? The first displacement was 3 blocks east, and my second displacement was 4 blocks north. So we actually just did vector addition. The resultant was 5 blocks, 53.1 degrees north of east. I just did vector addition. And indeed, when we can add any kind of vectors. It's easier to kind of wrap your brain around these displacement vectors because they're nice to draw and they're easier to visualize. But whether we're talking about acceleration, velocity, force, some of these more abstract vectors, or displacement, the more straightforward vector, the mathematics is exactly the same. So we add these by drawing the first vector, and then we draw the second vector so that the tail of the second vector is hooked to the tip of the first vector. And then the resultant goes from the tail of the first to the tip of the second. That's exactly what I'm going to demonstrate here, but a little bit clearer, I suppose, in my PowerPoint than on the chalkboard. Here's my first vector. I'm going to add b to it. Notice I'm going to draw it so that the tail of the second lines up with the tip of the first. A plus b equals c. C goes from the tail of the first to the tip of the second. The sum of two or more vectors is called the resultant. And that's exactly what we did here when we were talking about Jane and her little trip across town. Now, if this seems a little weird and abstract to you, it is. It totally is. And we're not going to have to deal with too much more other than a little bit of displacement vectors until we get to Chapter 3. And in Chapter 3, we're going to spend a little bit longer and slow down a bit and talk a bit more about vectors.